Okay, guys, let's go. Okay, now the first concept that I want to talk to you guys about, I'm not sure if it's at the bottom of page 16 or at the top of your page 16, but discussing the difference between mutually exclusive and independent events. Okay, so first of all, mathematically, let's see what I've shown you guys before. Mutually exclusive, having two events right here, and the probability of there being any intersection is going to be an empty set. Okay, or the probability of the occurrence is 0%. But let's talk about the idea of here, independent versus dependent, and independent versus not mutually exclusive. That's what I want to talk about. So here you have a coin, you have a heads, or you have event B, which is the number 2 on a die. Now, they are not mutually exclusive because it could happen that if you have both of those things in your hand and you throw them, then you can get a 2 and a coin. So let me restate that. It is possible, if you throw things simultaneously, for you to get a heads on a coin and the 2 on a dice. So it is not mutually exclusive because both situations can happen at the same time. But they're independent of each other because whatever I get on this dice has nothing to do with what I get on this coin. Okay? So now, next example. I passed my statistics final, that's event A. Event B, Sam went to Hawaii. Well, yes, they are independent because passing the AP statistics exam has nothing to do with him going to Hawaii. But are they mutually exclusive? The answer is no, because it is possible for him to pass the statistics exam and go to Hawaii. Now, I know what your thoughts are. Are they truly independent? Well, let's say that there's a parent that says, I don't care what happens on your test. You get to go anyway. And if that's the case, they are totally independent of each other. Let's look at another example. Here, third example, I have odd on a die and even on a die. Well, here, yes, they are independent because there is no way that you're going to get, well, the outcome of one die is not affected by the other. There's no way that you're going to get, if you get an odd on one, does that stop you from getting an odd on a second one? The answer is no. Are they mutually exclusive? The answer is yes. Because if this is one die, okay, and that's the key. If this is one die, there's no way you're either going to get an even or an odd. So being a little bit more clear on this situation, if there are one die, you throw a die once, okay, I got an odd. Well, next time I throw it, because dies, when the outcome of one's not affected by the other, okay, the second throw, I can get something completely different because the second outcome is not affected by the first. But here, there's no way with one die, that I can get both an odd and an even. Now, if there was more than one die, then that would no longer be mutually exclusive. But there's only one die here, and because there is one die, let me make that statement, it is mutually exclusive because you can't get both odds and even on one die. So here, let's make a note. One die. Okay? Now, I wanted to jump down and say events cannot be both mutually exclusive and dependent because if one event happens, the other one is guaranteed to happen, guaranteed not to happen. Because if one thing happened, then the other one is guaranteed not to happen. And from the fifth edition's perspective, two mutually exclusive events can never be independent because if one event happens, then the other event is guaranteed not to happen. Well, that's saying the same thing I just said, but slightly different. Now, let's do some of your examples. Go to your page, I think it's probably your page 15, number 80. Okay, so right here, we're talking about fundraiser. We have a tree. And here's the problem. Let me show you the tree in a minute. Okay, we want the probability of a person contributing to a charity. So we have this, this, and this. So this, this, this. So you multiply all of these together. Then you have this, and you multiply all of those together. And then finally, this. Okay, and you multiply all of those together. And then when you get the product of all of them, you add them up together. So as you can see, here are all of the values that I just showed you. And you add them together and you get the 0.224. Now, given, here's that formula. So remember it's saying that we have to find out what the two intersect, which was the 16% or the 0.16 over the grand total of all contributions, which we found right up there, and you just do the math on that. Okay, next let's look at problem 82. So go ahead and take a moment to read it. So pause. Okay, so they're asking me to identify the 50, whether the positive, the false positive, and the false negatives. Well, here you have the 50 out of the grand total, which is the 750 value right there, to give you the false positive rates. The false negatives, please recognize that they gave you right here the 250 minus 240 to get 10, and this is out of all the ones that have the condition. So that's where this came from. And as we look at B, take a moment, pause to read it, try it yourself. Okay, now you have the probability of having the condition and a positive result. So here, having the condition and positive result when both of them are happening. Remember, there's that formula again. Okay, over the grand total of everybody that's positive. And then there is your percentage. Okay, now let's talk about the Titanic. Okay, here, if you refer back to page 60, example problem 64, we look at the probability. We need to see the probability of survivors given that they're second class. Okay, so I sat here and wrote down this little table. The probability of survivors given that they're second class is 99. Okay, over all of second class, which is going across vertically. And then when you do the math, that is going to be your 36.2%. Yes, I had to correct that. Then we look at the probability of all survival. So here, this list, this column, I should say, are survivors. And then I'm going to divide that by the grand total to get this. So the idea of are they dependent or independent, there's a mathematical formula associated with that. Events are not independent because the probability of survival given that they were second class is not equal to the probability of survival. They don't equal each other. Yes, slightly different, but nevertheless they don't equal each other. So therefore they are not independent. We got to be careful of using the word dependent. It's kind of like saying not guilty does not imply you're innocent. It just says that there's no evidence to support the guilt. The same thing is here. There's no evidence to support the independence. Okay, as we continue on, problem number 86. Here, who eats breakfast? Refer to this problem. And I just wrote down what we needed. So this is either breakfast or not breakfast eaters, and M represents the males. So I needed to know here, to determine if they're independent or not, we're trying to see if these two equal each other. Now, we found out that they didn't. So I had to find the probability of breakfast given males, and here's your formula. And then, from there, this equals 0.5938. Then I had to find the probability of just breakfast, which you have here. And since these two are not equal to each other, that means that they are not independent. Next, problem number 90. As we look at problem number 90, okay, problem number 90. Here, remember, we're talking about, where does it say? Amongst the 10, there are 9 authors. Would you be surprised if none? Okay, so remember, here is 1 minus the probability of something not occurring. Okay, well, that's not true in this case. We're saying the probability of none. So here, if this is the probability of occurrence, and the probability of not occurrence is 0.904, and we're talking about it not happening to 9 authors. So the first author, the chance was 99.4%. The second one is 9.4%. Okay, I had to pause because some kids came in. Okay, so what I was saying was, okay, of 9 authors, we want to find the probability that none of them. Okay, so here, so if we have a 0.096% that it happened, 0.904 that it does not happen, and there's 9 cases in which it doesn't happen. Would we be surprised? No, because when you do the math on this, you can do it. It's pretty high, so it's not that surprising. Yes, I did take the time to do the math. Okay, now my last one on this page. Okay, lost internet websites. So if we randomly select 7 internet references, okay, what is the probability that at least one? So remember, this is 1 minus the probability of it not happening, but the probability of it not happening, we want 7 of them that will not happen. So as we look at this right here, that's 1 minus that here. This is 1 minus, let me put a little complement right there. It not happening, so it happened 13% of the time. It not happening is 87% of the time. So 1 minus 0.87 to the 7th power. And let me clean this up right now. Okay, so here the probability of it not referencing the Science Journal is 87%, and I'm looking at 7 different internet references. Okay, last problem, problem number 94, last problem of this chapter. Okay, so read it. So the question is, given these 4 flights, are they dependent or independent arrival times? Well, the reality is if one's late, it's going to affect the other. So this consistent is not happening. So, and I'm not saying cross that out because the values are wrong. I'm saying that if one's late, it's going to affect the other and the other. I mean, thank goodness we don't live in New York or Chicago, because they have these snowstorms, and yes, those planes are affected. So the answer is no, they're not independent, because one flight does affect the probability of another. One flight's arrival time does affect it of another. Okay, peace out, guys. I'm going to send you guys a reminder so you know what homework you're doing. Have a good one.